Hello everyone! In today's video, we're gonna be solving a combination problem. A problem that involves the concept of shear stress and the concept of normal stress. In this problem, we're given a structure that consists of two members, which are pin connected. Member AC and member BC. On member BC, we have an uniform distributed load applied throughout the member, and we're also given that the maximum normal stress the cross-section AA can withstand is 20 megapascals, and the maximum shearing stress section AA can withstand is 15 megapascals, knowing also that the cross-sectional area of the section is 100 millimeters square. Now that we have discussed all the given information, this problem is asking to determine the maximum uniform loading that can be applied to the frame without exceeding the given maximum shearing and normal stress. So let's get started. The first step on the solution will be to draw a free body diagram of member CB. This is because member CB is being affected by the distributed load, and it's also affected by the force of member AC. In this case, we're interested in finding a relationship between the axial force on member AC and the distributed load applied on member CB. Okay, once we have drawn the free body diagram of member BC, we see that axial force of member AC has two components, the X component and the Y component. Therefore, we need to break that force into components. Okay, so to break force AC into components, we need to use the ratio of the structure dimensions, so that the X component of the force will be the magnitude of the force times 2 over 2.5, and the Y component of the force will be the magnitude of the force times 1.5 divided by 2.5. Now that we have solved for the components of the force, we can go ahead and apply the equilibrium equations to the system. In this case, I will be summing all the moments about point B, since I don't want to find the reaction forces at B. I'm only interested in finding the relationship between the magnitude of force AC and the distributed load. At this point, I needed to convert the distributed load into a single point load. And the way I did that is by multiplying the W, which is the value of the distributed load, by the length of the member, which is 1.5. The only component of force AC that is creating a moment is the X component. Once that's clear, I added all the moments. Once I plug all the values, I get that the force AC is equal to 15 over 16 times the distributed load. Once I have that relationship, I'm ready to move on to the next step, to apply the two constraints that we have, the maximum normal stress and the maximum shearing stress. To apply the maximum normal stress and the maximum shearing stress constraints in this problem, we need to draw section AA so we can see how the axial force on member AC is creating internal loadings in member AC. Those internal loadings is the normal force and the shearing force. As stated in the introduction to normal stress and the introduction to shearing stress video, the normal force has to be perpendicular to the cross-sectional area, and that the shearing force has to be parallel to the cross-sectional area. Now that we have drawn the internal forces, we can go ahead and solve for the normal force and the shearing force. From here, we know that the normal force is the Y component of the axial force of member AC, and the shearing force is the horizontal component of the axial force of member AC. So in this case, using our dimensions on the triangle we had above, we can get the value of the normal force and the shearing force. In this case, the normal force is equal to 9 over 16 times the magnitude of the distributed load, and the shearing force is 3 over 4 times the magnitude of the distributed load. Now we're ready to apply those values into the normal stress and the shearing stress equation. Once we apply the value of the normal force and the value of the cross-sectional area and make that equal to the maximum normal stress, we obtain that the maximum magnitude of the distributed loading is 3,555.5 newtons per meter. We need to verify this value with the maximum shearing stress constraint, and to do that, let us use the maximum shearing stress equation. Here we know that the maximum shearing stress is equal to 15 times 10 to the 6 pascals, and that is equal to the shearing force, which is 3 over 4 times W divided by the cross-sectional area of section AA, which is 0.0001 square meters. We get that the maximum magnitude of the distributed load is 2000 newtons per meter. As we can see over here, the distributed load based on the normal stress constraint is larger than the distributed load based on the maximum shearing stress constraint. Therefore, in order for us to avoid failure in this structure, we need to choose the smallest maximum value of W. In this case, the largest intensity of the uniformly distributed load that can be applied to the frame is 2000 newtons per meter. And that will be our final answer. I hope this video has helped you understand a little bit better the process of solving a combination problem that involves shearing stress and normal stress in a member. If you find this video helpful, please don't forget to subscribe and give this video a like. Thank you so much for watching.